All right, we're back. So where we left off, we were looking at the different types of NoSQL databases, or the styles. You may recall we had key value stores, document stores, column stores, and graph stores. We ended by looking at a variety of different key value stores, and now we're at the document stores. Well, with a document store, data is stored as JSON documents, and JSON documents are, of course, hierarchically structured. In this class, of course, we've already had some exposure to this in our labs. We've already used MongoDB, but there are some other examples. As you can see, AWS has its own cloud database that's very similar to MongoDB. Google Firebase and Cloud Data Store also are document stores in some kind of way. And we can see with the contrast here, in a relational SQL style database, we break information up and we relate data using foreign keys and primary keys. But with the document store, the relationships, if you will, are implemented via hierarchy, through things being contained inside. Another type of NoSQL data store are column stores. And personally, I've had no experience with using these. I know Cassandra is probably the most popular one. And in a sense, rather than having records of data, you just have columns of data. I'm not completely sure how information is related between columns and how that actually works practically in Cassandra. But there it is. A new form of NoSQL database or graph databases or graph stores. And these are really, really interesting in that data is represented as a network or a graph of entities and their relationships. What does that mean exactly? Well, in an SQL database, relational database, relationships are expressed kind of indirectly through the linkage between foreign keys and primary keys. And sometimes you have these mapping tables or associative tables. Think about a many-to-many relationship in SQL. How do you implement a many-to-many relationship? Well, you have an intermediate table that contains just the two foreign key columns in the two tables. It's kind of artificial in some ways. But in a graph database, relationships are actual things that can be stored and queried. So as you can see here, the entities are these circles, and these entities have properties. But they also have relationships that connect the entities together. So you can see this person here works for this entity, lives in this entity, and owns one of those, And a given entity might be related to multiple other entities. So evidently, again, I don't have much experience with these, you can do some really intriguing and fast kinds of queries once you have information stored in these graph databases. As you can see, there's I think Neo4j, I've seen that one quite a bit, but I guess there's other ones, and Redis has its own graph databases. I suspect these are going to, I don't know, you get the sense that these are going to be, that these might be the next big thing. It's hard to say. Well, NoSQL databases, surprise, surprise, don't use SQL to query or modify the data. And as you've already seen, Mongo uses JavaScript, where we have this kind of, what looks like a kind of a frightening type of syntax, but it does more or less have an equivalent, is an equivalent to an SQL query. It just has a different syntax. All right, that's sort of NoSQL in the big picture. Let's take a look at a bit more about MongoDB and cover a few things that we haven't had a chance to really look at in our previous lectures or in our labs. Some of this as well will be familiar to you already from a previous lecture. But MongoDB, as it says, is an open source NoSQL document store database. There's no schema, and you package your data as JSON objects. By the way, Mongo itself doesn't store the data as JSON. That would be really inefficient and would take up a ton of disk space. It uses a kind of a binary version of a JSON object. Mongo, not surprisingly, has strengths and weaknesses. It's probably its biggest strength. Whoops, stinks and weaknesses. Right, that's got to be fixed. Strengths. Uh-oh, I bet you. Yeah, look at that. It's showing up on multiple pages. No! I guess I could just re-record this, but I want to go home for supper. All right, let's get back. It has not just stinks, but strengths and weaknesses. It handles huge data sets that can be spread across multiple computers. That one's a really big one, and we're going to look into that in a bit more detail shortly. In terms of weaknesses, well, this is an interesting one. I've said here just no transaction support. Sometimes that's a weakness, but we're going to see sometimes it's actually also a strength. So clearly, a lack of transaction support is a problem for data like financial data that needs reliability and consistency. But other types of data don't need transactions. For instance, most commercial sites maintain sort of records of what users have done. Every click, sometimes even every mouse move, though not so much the mouse moves. That's sometimes referred to as clickstream data. When you think of hundreds of thousands of users, that can be potentially a lot of data. That clickstream data or analytic data is typically fed into special data mining software systems, and you can use it to maybe improve marketing, try to better understand what your customers are looking for on a website. It can also be used to maybe improve the performance, like what are people trying to get at, all of that stuff's important. But from our perspective here, we're talking about Mongo, why this is important is that on a busy site, there can be a staggeringly large amount of daily clickstream data, right? For such data, like who really cares if some of the data, some of our billions of records that we're collecting every day is inaccurate or is spoiled or whatever. That makes no difference, right? What we're interested in is the size of the data set, and then doing some sort of statistical inferences based on all of that data. So in that particular case, we don't really need transactions, right? And because we don't need transactions in MongoDB for certain types of data, it means it can actually more easily handle really large data sets and store them. A SQL database, it has to exist on a single computer. Of course, it can be mirrored to other servers, but it has to exist there on that computer. This gives a limit to the size of the database, but it also means that your database server needs to be a really hefty machine, really expensive, large disk, tons of memory, expensive. If you're using virtual cloud services, say AWS, you still have the same problem. You have to rent out a very expensive cloud instance in order to manage your database server for a SQL database. But a Mongo database can be scaled out horizontally to clusters of what are sometimes known as commodity servers, right? These are relatively inexpensive server machines that you can buy in the hundreds. Within MongoDB, this is referred to as sharding. We'll look at what that is shortly. Oh, as in like right now. So, in a multiple server environment, you may recall we've talked about this at various times. We've got a whole bunch of web servers and a load balancer that shuffles requests to different servers. Well, one of the problems that is more of an issue when it comes to writing data or modifying data is what happens when you update a piece of data, right? And then later try to retrieve that update, and it might be on a different data server. So this is this problem. How do you ensure that the second retrieval sees this update? This broad problem is sometimes known as the problem of data replication and synchronization, and it's a real computer science type problem. There's a lot of really interesting solutions to it. But this problem becomes really acute once you start distributing your data, not just across multiple servers, but across multiple data centers, right? You remember earlier in the semester we talked about content delivery networks and how you might have a site replicated at multiple data centers across the globe. How do you make sure an update, in Canada is seen by the people in France, right? That's a real issue. So there's, generally speaking, two solutions to this problem. One of these is known as single master replication. Okay, so here, of course, what we have is a single master. This, in a sense, is what this is like your single point of truth in some ways. So any web applications that change the master data set has to get propagated out to subordinates, in a sense, they're not exactly duplicates, but they're replicas. So the data is owned by the master node, and these replicas are read-only, right? They rely on the master to push out updates. So this is why it's called single master replication. So again, this master could be, in London, while the subordinates could be in France and Argentina. There is a problem, of course, with this architecture, and that is you have potentially a single point of failure, right? So you typically need to do something else with single master, and that is failover clustering. So in a sense, you have to have backup masters. So any change, and these would all be in a sense, within the same data center. And these passive masters would only be used if the active master fails or is taken offline for maintenance. All right, remember I mentioned there was two approaches. The second approach is to use something called multiple master replication. So in this approach, each replica acts as a master. So as you can see here, it looks somewhat similar in the sense that modifications are propagated out, but there's multiple masters. So if something, so the idea is that other web applications can access all these different masters. The problem is when a change gets made, it has to get replicated out to all the other masters. Well, Mongo makes use of single master, the very first one we looked at, but it uses a neat technique called sharding, which refers to the splitting of large data sets across multiple sets. So for instance, here we have a web application saying, hey, I want this data item, okay? And here's another one saying, hey, I want a different item. So we've got a special machine called a query router, right? You can think of that as a subsystem within Mongo. And the data, instead of having like a regular SQL database, which is one, in a sense, large, it's not exactly a single file, but you could think of it conceptually as a single file. But with Mongo, that large data set can be split across multiple shards. And then each shard, you can see, uses single master replication. So in this example here, instead of having a 75 gigabyte single database, you can see that there's three 25 gigabyte databases. And so we've sharded, we've broken up this large complex database into multiple ones. All right, I've upgraded my my video count, so I should be able to go over 15 minutes. So here I am, just a few seconds away from going over the 15-minute mark. So if this works, we'll keep going. If it stops, we'll know it didn't work. Oh, looks like we're still going. All right, which is good. So this is how Mongo is able to break up a gigantic database that really couldn't conceivably be held in one machine across multiple machines. I think it's a really kind of a cool technology. And I think it's kind of the type of thing that's, would make a good final exam question, right? Trying to understand this. Oh, actually, look at that. We're all done. We're all done. I'm not going to sort of talk about, how you actually work with Mongo. At least not right now. It's almost 7 p.m. already. I've been working on this lecture for like 6 hours. Or no, I think I've gotten a little better. I think it was only about 4 hours. Still. Anyways, that's it for now.